Here's a really interesting problem that actually gives us a technique that we can use on a lot of different problems. So let's go ahead and handle this, and it also brings up some conceptual interesting points here. So what would happen if I inserted a conducting slab between these two capacitor plates? Now, we cannot have our conducting slab touch either of these surfaces because that would actually create a short circuit. But we can insert it so it's maybe between them without touching them. So let's just say that there's a charge Q on this capacitor, and as always, we'll say the distance between the plates is D. So what I'm going to do is I'm going to insert a conductor of width A. Now the first thing you might want to think is what will happen when I'll have I'm just going to start with it right here, and this is a width A across. Would there be a repulsion or attraction or neither for this thing, this conductor, for this situation right here? Well, the conductor becomes polarized, right? And you get a bunch of negative charges up here and some positive charges here because of the polarization due to this external field right there. That external field gets polarized, so it's attracting. So what will happen is this conductor actually will fall into this. It'll get sucked in, and that's where I'm going to draw it right now. There, it's been pulled in, and I'm going to draw in all the fact that it's been polarized here. Now, very similarly, in a lot of ways, it's similar to a insulator put in there because it's making the field weak. The one difference is the field is so weak. What is the strength of the field in here? Once it reaches electrostatic equilibrium, the field is zero. There is no field there. So you might think, oh, okay, it's just like a dielectric. It'll make the capacitance greater. But there's another factor here. Not only have we reduced the field, we've actually made the field zero here. And we've done something else. We have, because the field is zero, the delta V is going to be different from here to there. We've changed the delta V because delta V is equal to ed, but that'll work for this part from there to there. It'll work for this part from there to there, but we can't count this middle part in our D because the field is zero in there. So this creates a couple of different interesting things that might increase or decrease the capacitor strength. So here's how we can solve this. This situation right here can be redrawn like this. Well, first of all, this is width A right there. So I'm going to actually redraw this. This is identical to, this situation I've drawn right here is identical to this situation. Here's my original capacitor plates, there and there, that far apart. But what I've done is I've introduced like more capacitor plates. Here's this right here. That's just the one surface of my conductor in the middle, and here's the other surface of my conductor. It's as if I've put two capacitors in series. Now, okay, still a question though, because now you might say, oh, well, capacitors in series, well, that will decrease the overall capacitance. But how have I changed my capacitance? My capacitors, I mean. How have I changed them? Notice that the new space between them is less. Now, if this is D right over here, this is D, and this is A width right there, I'm going to assume that I'm going to put this right in the middle. It turns out it doesn't matter if you do that or not, but if I did put it right in the middle, what would my new capacitors be? Well, notice that this is D minus A over 2. That's that distance right there. Here is D minus A over 2 also. So what I'm going to do is I'm just going to use the capacitors in series equation. Now, if you're wondering how I got d minus a over 2 right there, it's just a matter of the space. If this thing is d wide and it's taken up by a wide of a conductor, what's left is d minus a, and I split that into 2. Turns out that it doesn't matter where you put this slab in there. All I got to do now is take a look at these two capacitors, which are now in series, and figure out what the equivalent capacitance of that is. So my equivalent capacitance right now, C equivalent for series, is equal to 1 over C1 plus 1 over C2. I'm calling this first one C1 and this second one C2. And then I'm just going to rewrite that again, equals 1 over the, if it's a flat plate capacitor, it'll be epsilon naught times A over D. But what is D? D is the space between the plates. So right here, that space is just D minus A over 2 quantity. And then that's C1 now, and then I got to do plus 1 over C2 will be epsilon naught A D minus A over 2. And you may say, well, don't you have to change, you change D, don't you have to change A? I don't, because A is just the plate area. Notice that's just the area of one plate. That is not changing. That's the same thing over here as it was before. For both of them, the plate area is identical as it was before for both of these. So I don't need to change A. And basically, I'm done. All I got to do is simplify this whole mess right there. And when you simplify that, what you get is as follows. Simplifying, you get C nu is equal to, it comes out to be A epsilon naught over D minus A. Now, so we can see there's two factors here. One is that we have them in series, so you think that would reduce the capacitance because you're putting capacitors in series. That's true, but we've made the distance smaller. So when we look at this, does this increase or decrease the overall capacitance? Before the C old, let's take a look at that. What was C old? Well, that was just A epsilon naught over D. Is this new C, looks like cold, is the new C higher or lower than this? Well, because it's a smaller number on the bottom, this is a larger capacitance. It increases the capacitance to put a conductor in there, which makes kind of sense because if we put an insulator in there, it would also increase the capacitance. But you do have to be careful here. The capacitance starts to get really, really big as this thing fills up more and more of this. In fact, if you had it filled up all the way to there, your capacitance would be very high because this D minus A part would be very small. And what happens if you filled up the entire space? Well, two things. One, the equation blows up because if D equals A, this would be 0 on the bottom. That's not possible. And besides, it would become a conductor and it wouldn't be a capacitor anyway. So both the physical and mathematical situations prevent A from ever getting as big as D. Now, you may remember that what I said earlier was it doesn't matter where you put this conductor. Let's take a look at this solution right here and see what the physical meaning is. We're seeing that the new capacitance is epsilon naught times A over what? Usually it's the plate interplate distance right here, the plate separation. What is it now? D minus A. What's the physical meaning of that? And how does that tell us that this problem could have actually been solved much easier? Well, if you look at this picture right here, all we've really done by inserting this conductor is created a new capacitor with a much shorter plate separation. In fact, the difference, it's taken A away, our conductor is A wide, is just new plate separation D minus A, and this is the exact capacitor equation, epsilon naught times A over the plate separation, and that's all D minus A is the plate separation. So there was actually a much, much easier way to figure that one out.